He will be speaking about a homological theory of functions.
Hello, can you guys hear me?
Yes.
Can you guys see me?
Yep.
Yep.
Great. Yeah, so thanks for the invitation and thanks for the very nice workshop. Today I'll talk about a newer topic called homological theory of functions. And this is based on two papers, one paper by me in 17, and then a joint work with Justin Chen, Chris here, and Meng Yuan, all ex-Berkeley people, well, 2 years ago, I guess. Yeah, time goes fast. So let me just jump in right away. And this topic is at the intersection of machine learning and algebraic combinatorics. So let me actually do a more like popular science kind of intro on this topic. So how many of you have heard of AlphaGo? Like who has not heard of AlphaGo? Raise your hand. Okay, good. So this is like the like kind of the eureka moment where machine kind of unexpectedly defeated the world champion in Go, which is like a very, very difficult problem in artificial intelligence that was not expected to be broken within 10 years, like probably more than that. But it was a very unexpected breakthrough. At the time, it's a very good the event was also very popularized around the world. And in fact, like there's rumors saying that because of this particular event, China now like puts 100% of their weight behind AI, and there's like now a geopolitical situation. But that's for another topic. Okay, how many have you seen stuff like this, where you want to like make a website and you don't know how it codes, so you just type in some text that in natural language describes what you want to make, and then the machine just spits out code for you. So this is done by GPT-3, so which is like one of the biggest language models that exists right now, which essentially predicts the next word given the previous word, but you can refashion it in a way that really makes your jaw drop in some sense that we're at this capability. So these two examples are some of the most prominent examples of recent advances in artificial intelligence, and it's a technology called deep learning, which is essentially using neural networks to learn certain patterns in nature from a large amount of data. And if you talk about if you go beyond neural networks and talk about general machines that learn from data, this is called machine learning. And then finally, like a broader discipline is artificial intelligence, which is just like use whatever technique can. So maybe you can do planning and calculations other than learning from data to achieve some kind of intelligence. So today I'll talk about the intersection between machine learning and algebraic combinatorics. So, I assume most of you, have some basic knowledge in combinatorics. So I'm actually gonna just delve a little bit into the basics of machine learning before I move on to connect to algebraic combinatorics. So what is machine learning? So I don't know how many of you have exposure to this, but basic desire of a user machine learning is that you want to automate some task which has been done by humans in a very costly way. So for example, suppose you want to make a hot dog detector. So you use an app, if you point your phone at a whatever, it tells you whether it's a hot dog you're pointing at or it's not a hot dog. So for example, this is like a demonstration of what the app would look like. And the way you would train such a hot dog detector is you have data sampled. So you collect a large amount of data, and the data includes essentially a bunch of pairs where each pair consists of the input, so like an image of a hot dog or not hot dog, and the human label saying it is a hot dog or it's not a hot dog, right? So it's like a bunch of examples. Essentially, we want to learn a function that would interpolate and extrapolate this data. But to do so, we need to guess kind of the form of the function that will make sense. So for example, you could guess, okay, like a linear function probably would do just fine. Or we can say, oh, maybe it's more complicated, like a neural network. And when you specify a form of the function, you're specifying a function class, right? Within which you can look for the right function. So here's like a pictorial, representation of a 1D to 1D function class, a bunch of sine curves of different phases. And so finally, you want to use some optimization technique to find the function that fits the data the best and can extrapolate to unseen data. So maybe it's this curve that fits the data the best. Okay. Also, if you have any questions, feel free to shout it out. All right. So you can ask, why can't we just be lazy and put all the functions in this class C that I was just talking about? Can we just find the optimal one within all possible functions? And as you can imagine, this is a really giant class, and you cannot efficiently find the right function in terms of number of examples needed, or in terms of computation. But there's but for the topic today, I'm going to focus on efficiency in the number of examples, labels needed. And then you can ask, okay, so maybe all functions are too large, but for practically occurring C, so function class C, can we find the right interpolating function and extrapolating function efficiently? And the answer is yes and no, depending on the class, and we'll see some examples later on. And in classical machine learning theory, one central question to ask is, for which function class C can we find such a function, the fitting and extrapolating function efficiently, right? So in other words, for which function class C do we need only a few random samples to learn the right function? So tying back to the example of hot dog detector earlier on, the data set is again a bunch of pairs, each pair consisting of an input image and the label of hot dog or not. And you want to use as little data as possible to learn the right function, because if you're doing a startup, more data means more collection, means more cost, right? And you want to lower your cost. Okay, so the fewer the better. And again, the question is, like, for which function class C can we do this in the fewest number of samples possible? So in classical machine learning, there is an answer, and I'll tell you about it. But the topic of today is that it turns out the answer is also that the C that have this property are the Cs who have simple homology. And this is kind of a remarkable statement because, like classically, machine learning has never really touched algebraic topology in really any way. And here we have some kind of like really surprising characterization of, efficient function classes using homological techniques and homological statements. So it's really kind of like, Europe reached America for the first time, in some sense. All right, so now let me tie back. Let me describe how do we go from learning to topology. So again, in machine learning and in computer science in general, we're actually mostly concerned in theoretical communities with function classes. So for example, in learning theory, we're considering function classes from which we want to pick the right function that fits and extrapolates the data. In computation complexity, we consider classes of functions of some kind of difficulty of computation. And the way we're going to use a topological analysis or algebraic combinatoric analysis is we're going to associate topological space to the function class, not to specific functions or like just the input space, but like we're going to associate the topology to the function class itself. And we're going to analyze this topological space using some tools like combinatorial algebra, Stanley reasoner theory, and cellular resolutions. So I won't go into a lot of detail. I don't have time to go into a lot of detail on all of these techniques, but I seek to give you kind of the brief overall idea in how do you tie these two kind of disparate fields together in the context of learning theory. And I'll speak a little bit about computation complexity at the very end, but mostly I'll focus on learning theory. Okay, so now I'm going to define what is the topological space associated to the class. And I'm going to introduce a little bit of notation. So bracket n means the set from 0 to n-1, so there are n elements. And then bracket n to m means the set of all functions from n to m. Okay, so the way I'm going to define this topological space is as follows. If C is a class, a subclass of all the functions from n to 2, then we associate the complex SC, which is simplicial complex, and it has vertex set given by the product n times 2. So there are 2 n vertices, and you have one facet for each function in the class. And the facet has vertices given by the graph of F, right? So I am not, putting a topology on the set C, but rather I'm associating it in a kind of a dual way. All right, so let me actually delve into some examples to flesh this out. So let's look at a very, very simple example first. Let's look at the function class from 2 to 2. So for the input space is 0, 1 and output space is 0, 1. There are 4 such functions. Here, each row represents a different function, and I've named them the top, bot, identity, and negation function. So top essentially sends everything to 1, bot sends everything to 0. Identity is identity, negation is obvious. Okay, so now let's look at how the construction goes. The vertex set is n times 2. And we're gonna, so there are 4 vertices in this case because n equals 2, and we're gonna label them by the, so we're gonna label them by these notations, which means like 0 maps to 0, 1 maps to 1, and so on and so forth. Okay, and each facet is gonna have the vertices given by the graph of the corresponding function. So for example, identity is going to have, it's going to be an edge between 0 maps to 0 and 1 maps to 1 because they describe the identity function, and so on and so forth for the other ones. So you can notice that this forms a diamond, and it has a non-trivial homology. First homology is non-trivial. And okay. So let me just give you a slightly more non-trivial examples to, again, continue fleshing out the definition. So you can consider instead of 2 to 2, the set of functions n to 2. Then in general, the complex S sub n to 2 is an n orthoplex, which in 3 dimensions looks like this. And this means that it's the boundary of the convex Hall of the coordinate vectors, plus or minus coordinate vectors in Rn, right? Okay, so homologically, this is a sphere, and the n-1 degree homology is equal to z. But for more general non-trivial C, like strict subclasses of the full class of functions, S sub C is a subcomplex of an orthoplex, which is obtained by picking a subset of the facets and looking at the subcomplex generated by the subset. Okay, so this is the final example, just to look at something more non-trivial, not just like an orthoplex with a non-trivial homology. So here, let's look at F2 linear functionals. So here, the input space are the non-zero column vectors in F2 squared. So there are 3 of those. And the function class is the set of linear functionals, which you can think of as row vectors in the dual space of F2 squared. And this table shows you the graph of these functions. So in each row, we have a different function. Like the left column are the names of the function, which are represented by row vectors, right? And these entries signify the values of the function taking on different inputs, where each column corresponds to different input, right? So for example, the 0, 0 function sends everything to 0. The 0, 1 function, sends 0, 1 to 1 because the inner product of those 2 things is 1. Okay, so we're going to look at the complex associated to the space of functions. And so it looks like this. So again, it's a subcomplex of the 3 to 2 complex, which is the orthoplex in 3 dimensions. So that's why this kind of looks like, this looks like a subcomplex of the orthoplex given by the subsample of the facets. And each facet is a triangle where, for example, the 1, 0 facets has the vertex 0, 1 to 0, 1, 1 to 1, and 1, 0 to 1, because those are the values of the function. And if you can like visualize this better by using an animation. And so in short, it looks like this complex looks like the choosing every other facet in the orthoplex in 3 dimensions. Okay, so here the homology is not just a sphere, right? It's you can see that the homology is a z3 z to the 3rd power in the 1st degree and nothing else. All right, so hopefully that gave you some idea of what the complex looks like and how it's defined. Let me pause here for any questions. All right, sounds good. So now I'm going to actually tie back and talk about the connection between homology and learning. So the statement I want to eventually make informally is the following. So the amount of data needed to learn an unknown function in a class C is controlled by the homology of C. So by homology of C, I mean like the homology of the complex associated to C. And going a level deeper, I want to say that the amount of data is controlled by the highest dimension of any hole in C. So in other words, like kind of something like the highest non-vanishing degree of the homology in C. But this is actually not quite right. So let me just define one more thing: the link of a subset in a symmetric complex before I finally come back and give you the full statement. But so the link of a subset of vertices inside a symmetric complex is essentially the set of faces that are disjoint from the subset, but whose union with the subset lie in the complex. So this is kind of a mouthful and maybe takes a second to digest. So let me give you an example. So in the complex I just described in two dimensions, we can look at the link of the vertex 0 to 0. And so essentially we're going to look at the cone, which is the subset of the complex given by the cone with the vertex as 0 to 0, which is essentially adding in these two vertices along with the connecting edges. And the link is just the base of this cone. So these 2 points. Okay. And more generally, you can look at the link of any subset, not just a singleton. And the intuition is that you're going to look at a kind of a cone generated from the subset, and then you look at the base of that subset, the base of that cone. Okay, so the more precise statement is that the amount of data needed to learn an unknown function in class C is controlled by the highest dimension of any hole in C or any of these links. And the reason we look at links instead of just the homology of the complex itself is that you can kind of add triviality to a function class by saying like all functions map 0 to 0, and that would change the homology of the parent complex associated to the class by essentially adding a vertex, which is a cone vertex over everything else, which trivializes homology. But if you look at all of the links, you can remove the triviality, and this definition makes a lot more sense. So we define this as the homological dimension of C offset by 1, and formally it's given as follows. So the homological dimension of a function class C, dim HC, is defined as the max over I, where the ith homology is not zero for some link in the complex plus one. Okay, so far I'm just defining the complex and the homological dimension, and shortly I'm going to tie it back to learning theory. But any questions so far? So hopefully this should be all quite natural to like they're quite natural definitions.
Oh, so there's a question in the chat. Yuan asks, given your relating class of functions to homology, does it make sense to speak of the homotopy type of the class of functions?
Yeah, it definitely makes sense. But I haven't calculated it. I am not sure. My intuition is probably pretty hard to calculate, especially these complexes are like really high dimensional. And so like a lot of the classical techniques might fail in the setting. And the way, I've been able to kind of like handle the homologies through like Sandhi-Reasoner theory and like kind of look at the cellular resolution of the Sandhi-Reasoner ideal. Yeah, it's a good question. I don't really know a good answer to the homotopy type of the complexes.
Okay, thank you.
Mm-hmm. Okay, so now I'm gonna come back to the other side, the learning theory part, and I'm going to define this thing called the VC dimension, which is a classical notion in learning theory, and it relates back to the number of samples needed. So the VC dimension of a class C, which is a subset of n to 2, is defined as the max max cardinality of a subset U of the input space N, such that the restriction of C to U is equal to the entire class of functions on U, right? So U to 2. So this is again, kind of like a very condensed definition. It might take you a little bit to grok it, but essentially we're saying, like what's the subset on which C essentially describes all of the possible ways to yeah, all the possible functions on that subset. And we say C shatters U if the condition above is satisfied. So I'll come back to this a bit later. And it's a classical theorem in learning theory that the number of samples needed to learn the correct function in C is the most constant multiple of the VC dimension of C. Okay, so this is just one slide on some basic background in the classical learning theory. So now let's put it all together. So why would homology matter in learning theory? And the key theorem is that the VC dimension is bounded above by the homological dimension of C for all possible function class C. And probably I think that itself is kind of remarkable, but the more surprising thing to me is that for a lot of different classes of functions, you actually achieve equality. So these are some examples where they occur very commonly in classical learning theory. So polynomial thresholds or monotone conjunctions, so on and so forth. You can look at these. And you have equality of those two quantities in all of these cases, which suggests that there's like something fundamental going on. But in general, they're not actually equal. So we cannot hope for a tight coupling between those two things. But the fact that they're equal for like a lot of things, a lot of classes of interest in learning theory is very, very interesting. Okay. Okay, so now this is the last slide on the learning theoretic part. But I'm just going to talk about like what kind of math goes on behind the scenes. So how do we prove the inequality I discussed earlier, and in general, how do you go about analyzing the situation? So like I said, C, the VC dimension is defined as the size of the largest set U that is shattered by C, which means that if you restrict the function class C to the subset U, then you're gonna get back all of the functions on U. Okay, so the first step of the argument is that C shatters U if and only if the complex restricted to U times 2 is isomorphic to a sphere of dimension U minus 1. So this is fairly straightforward. So for example, in this example, we can look at like the 0, 1 to 0 and 1, 0 to 1, and we can look at the middle rectangle square in the middle, and you can see that like because this this function class shatters the 1, 0, 1, 0, 1, 1 subset, the subcomplex here in the middle is a diamond, which is homologically a sphere. So this is a equivalence. So C shatters U if and only if the restriction of the complex to U times 2 is isomorphic to a sphere of the right size. And then the second step is now we introduce homology. So it turns out that this is true if you make the statement that S sub C restricted U times 2 is homologically sphere if and only if it's homeomorphic to a sphere. And then finally, you want to say that the subset U, so again, U is any subset that C shatters, and you want to say that this set has cardinality at most the homological dimension C via machinery insanity reasoner theory, which I don't have time to go through in detail, but essentially what you do is you look at the phase ideal of the complex, which are essentially encoded by monomials, which correspond to non-phases in the complex, and then you look at the dual ideal of this guy, and then you want to essentially look at the you want to resolve this ideal and look at homologies, and this homology relates back to the homology of the origin complex. So unfortunately, I don't have enough time going through this in detail. So so that's all I'm going to talk about the intersection of learning theory and algebraic topology or algebraic combinatorics. Any questions here? Okay, so the last couple slides, I'm just going to briefly go through some other kinds of results in this intersection of algebraic combinatorics and theoretical computer science. So one application is in complexity theory. So in complexity theory, you study complexity classes, which are function classes defined by difficulty of computation. So for example, P is a very famous class of functions, which is defined by saying that the function in the class have polynomial runtime in the size of the input. And NP means the set of functions for which the answer can be verified in polynomial time in the size of the input. And computation complexity studies the relationship between these different complexity classes. And the most famous problem within which is the P equals NP problem. And our work provides a homological invariance for complexity classes. So like if you want to show P is not equal to NP, you might be able to show that they have different homologies. Of course, it's still very hard to show, but just as an example, this is kind of the strategy. And in our work, we demonstrate this homological technique by separating classes, the class of polynomial threshold functions from the class of parity functions. And essentially, the idea here is that if you add the parity function to the polynomial threshold function, you can show that like there's a homology that is killed by this action, and as such, like the function classes are different. And some other results are as follows. So a function f is a polynomial threshold if and only if f kills the homology of the class of polynomial thresholds when you add the function to the class. Another one is that fitting a polynomial threshold function has no spurious local minimum. And finally, I think something super interesting is that this homological theory functions is a homological theory of specific kinds of co-sheaves, which are in spirit dual to the sheaf cohomology. And this has relation to like probabilistic random function classes. So some of the open questions here are as follows. So can we exactly characterize when homological dimension equals VC dimension? I think this is a really beautiful question, but it might be out of reach at the moment. Another question is what data does the Euler polynomial and the Hilbert function of the complex tell us about the function class? And what other complexity separations can we prove using these homological invariants? And finally, can we use the co-sheaf perspective to extend our results to randomized complexity classes? Great. And that's it. Thank you. These are the 2 papers involved in this talk. Feel free to look them up, and I welcome any questions.
Okay, so let us thank the speaker for a great talk. And feel free to unmute yourself and ask questions or type them in the chat and I can read them out.